second presentation by Tarique Anwar from Swinburne University of Technology in Melbourne, Australia. And his paper is, as hopefully you can see on the screen, is Temporal Tracking of Congested Partitions in Dynamic Urban Road Networks. So thank you, Tarique. The floor is yours.
Okay. Thank you, Ali. Thank you for introducing me. Now, first of all, I would like to thank the TRB Artificial Intelligence and Advanced Computing Applications Committee for selecting our work as one of the candidates for this webinar series. And a very nice presentation was given by Kim in the first presentation. Basically, that presentation was mainly on analyzing the traffic congestion and predicting the traffic congestion and identifying its relationship with other weather conditions and other factors using probabilistic methods. In our work, it is basically about identifying and tracking the evolution of congestion in real time based on real-time traffic data. So we are not going to do any kind of prediction. It is just about analyzing how the congestion is evolving over the period of time. My name is Tarique Anwar, and this work has been done with Professor Hai and Professor Chengfei and Professor Serge. So here I start my presentation, and the outlines are as it is shown. Firstly, I will introduce the problem, the scenario, and then we'll go to the research problem. Then we'll move on to some preliminaries required to understand the proposed framework. Then I will show some interesting results. Finally, I will conclude this talk. So these days we see the trends are that people migrate from rural areas towards urban areas, and as a result, this increases the traffic load on urban road networks. As a result, this road network keeps on growing in its size. The traffic congestion is also increasing. According to a study, the avoidable cost of congestion in Australia is projected as $20.4 billion by 2020. Now, this cost is avoidable, which means that in some way, if we try to optimize the traffic flow, this cost can be minimized by developing smarter ways to handle the traffic management. Also, we can develop smarter services to provide better services for the commuters so that they can plan their journey in advance, or they can use the real-time traffic scenario to understand and decide their journey. Now, here in the slide, I have shown the road network of Melbourne, which is partitioned into 4 different sub-networks. Here we see that there is one big partition, and there is in the CBD there is one small partition which is highly congested at a point of time. So basically, we mean that by congestion we mean that it is a sub-network which is spread in a region, and which includes several road segments in that region where it has affected. And the pattern that we see generally is that this congestion keeps on moving over the period of time. So in the morning, this congestion starts forming in the outer areas, which keeps moving towards the city center in the day, keeps inside the city center in the day. Then again in the evening hours, when the office starts closing, people start moving outside, and the congestion starts moving back towards the outer areas, which now we can actually develop methods to track these congestion locations to enable a better network management. This can aid in 2 ways. First, it can aid in providing better network management by the traffic authorities. Second, it can help the commuters, the daily travelers, to plan the journey by understanding the traffic movement. So our research problem is to identify and track the congested partitions over a period of time. Basically, we first start with partitioning a road network so that we get different subnetworks which have homogeneous congestion inside, but they are very different to the congestion occurring in other subnetworks. As I showed in the previous slide, in the figure, that there were 4 different subnetworks, and each of them had a homogeneous congestion inside, and they differ from each other. Basically, we start with partitioning the network in the beginning. Then we incrementally update those partitions at each new time point. One way is that at each new time point, as the traffic changes, we can partition the network again and again and see how the partitions exist in the network. But that doing that is a computationally expensive task, and we may need to invest a lot of time in doing that, which may not be able to handle the real-time traffic data as the new data comes in. So instead of doing that, we just incrementally update the partitions, because the changes doesn't happen all of a sudden. The changes gradually, the traffic changes gradually, and we just keep on handling that change to update the partitions. Then in the third step, we identify the congested partitions among them. Say we have got all the different partitions at the point of time. Now we want to identify only the congested partitions, as we are more keen to look into the congested partitions. So we define certain measures to identify when can we say that that partition is congested. Then finally, when we have identified these using statistical measures, then we visualize them on a map in different layers. So overall, it is a framework that I'm going to explain in the following slides. So before I move on to the proposed framework, I want to mention briefly about the traffic data that we are using. This traffic data comes from the traffic control system, SCATS. There are several different traffic control systems that exist in all over the world, and the 2 most popular of them are SCATS and SCOOT. In Australia, SCATS is used for monitoring these traffic signals, and we use the data collected from these SCATS signal sites from Melbourne network. Thanks to Vic Roach for providing us with this data. So specifically, the data that we consider are the volume data, which is the count of vehicles on each road segment at each point of time. Then the second measure is equivalent count, which is the estimated vehicle count. It is computed from some other measures, and not the exact count of vehicles. And then the volume ratio gives the ratio of estimated count to that of actual volume. So whenever this volume ratio goes above 1, it indicates an oversaturated traffic based on previous studies and also our experimental study. There is another measure called the degree of saturation, which means the proportion of effectively used screen time. So basically, when this measure is high, it means that the screen time has been highly used and indicates a high traffic load. So in our method, we will use 2 traffic measures: the volume ratio and degree of saturation. For both of them, a high value indicates a high traffic load on a road segment. Here I have shown 3 figures. In the first figure, it is the actual road map. In the second figure, the corresponding road network is shown. In the road network, we see that the road segment, each road has two directions of traffic flow, and each of the traffic flow direction is considered as a road segment in the road network. So because the traffic generally in the two opposite directions are not the same. In the morning hours, the traffic moves towards the city. In the evening hours, the traffic moves outwards. So the traffic is not the same, and both the directions need to be considered separately for the traffic to understand the traffic load on them. In the third figure, to resolve the issue of direction in the road network, we actually transform this road network into a form of graph, which is shown in figure C. So for each directed traffic flow, we consider them as a node in the road graph. And if any two road segments have a common intersection point, we create a link between them to establish a relationship, which is the connectivity relationship. That means a traffic can flow from one road to other. So in this way, we generate this road graph, and then our following method applies on this road graph. To define the road network, it comprises with a set of intersection points and a set of road segments, where each road segment has certain traffic measures associated with the road segment. Then in the road graph, we have nodes and links, where each node has certain feature values which comes from the traffic measure of the corresponding road segment. And here we go on to the proposed framework. Yeah, so it shows a high-level picture about what our method is going to do. We see in the corner here. Yeah, this is the SCAD system from where the data comes in. In the beginning time point t0, in the first time point, we partition the whole network, and it is the only time that we are partitioning the whole network. After that, we just incrementally update in this module here. So firstly, we transform the network into the road graph, as I mentioned before. And then after on this graph, we apply partitioning of this graph, and the partitioning algorithm is AlphaCAD, which has been published in the conference ADBT in the year 2014 by us. And then at each following time point, as we see here, ti plus 1, it goes on like that. As at each new time point, the data comes in, and we incrementally update the partitions available from the previous time point. So how we do that? There are a set of steps that we incorporate to do this, that I will further explain in detail in the following slides. And then after we have incrementally updated those partitions, we identify the congested partition and track their evolution. So basically, we extract first from these subgraphs, we transform them back into the form of road network, and then visualize them on a map. So this is an overview of our framework, and now in the following slides, I'm going to explain them in detail. In the initial partitioning step, our objective is to split up a large urban road network into disjoint partitions. And the properties that these joint partitions will have is that they will have high intra-partition homogeneity, and high inter-partition heterogeneity. So basically, it is trying to identify the differently congested partitions in the network. In the network, and a formal definition of this problem is here in the second part. So it is the problem is to group the set of road segments into a set of partitions, such that The union of all the partitions gives all the nodes, which is again the set of all the road segments, which means that there's all the partitions covers the whole considered network. And the second condition here is that there will be no intersection between any two partitions, which actually refers to the condition of disjoint partitions. Which actually refers to the condition of there will be no overlapping between any two partitions. Then each partition is connected inside. If it is disconnected, then that means there are multiple partitions. So to be considered as one partition, it has to be connected, and all the adjacency relationships that are existing in the road graph needs to be maintained in the partitions, except the cross partition relations, which will be broken during the partitioning. The condition, the further two more conditions are the cost of partitioning is minimum and partition volume is maximum. By cost of partitioning, we mean the overall weight of interpartition links that are to be broken during the partitioning. So we want to incorporate we want to have minimum weight of links that connect different partitions. And we also want to have high weight within the partitions, which actually refers to the condition of intra-partition homogeneity. Okay, then here we start with the road graph. V refers to the road segments, and E refers to the connectivity between the road segments. And the feature values that we consider is of this vi dot f. Vi is a node in the set V. And the feature value is actually a vector. We consider it as a vector, and it comprises two values. First one is the degree of saturation of this road segment, the corresponding road segment. And the second one is the volume ratio of the same road segment. And we define weight of each link in in the set E by this measure, which is the Gaussian similarity between So if the link is Wi and it connects two nodes which are Vp and Vq, then we define its weight by the relation by this Gaussian similarity between these two nodes. So this is just the Gaussian formula, and this is the variance, which is further detailed here. Now the K-way alpha cut algorithm that we use in this work, just a brief explanation about how it works. Now we are working on the road graph G, and we have its adjacency matrix A. Let us suppose that the partitioning of G yields this set of partitions, this set of K partitions, and let us define a function W, which is the sum of weight of all links between Pi and Pj. Then the objective function in this alpha cut algorithm is to minimize this function alpha cut P, where this function is given here. Okay, this weight is the summation of weight of all the links between Pi and Pj. Now, in this alpha cut formulation here, there are two parts. First one is considering the weight between Pi and all the other partitions except Pi. So basically, it is considering the inter-partition weights, and we want to minimize this similarity, this with this value, and we want to maximize the weight within its own partition. That means the summation of all the links within its own partition. We want to maximize this value. So we want to achieve partitioning in such a way that minimizes interpartition similarity and maximizes intra-partition similarity. To achieve this, we have developed a spectral clustering-based solution, which is detailed in this in the paper EDPD 2014, referenced in this paper. So, if you are further interested in that solution, you may have a look into that work. In the current work, we have just used that algorithm, and I am going to move on to the next step now. And the next step is how we incrementally maintain those partitions. Instead of repartitioning, as that is a computationally expensive task, we want to just incrementally update those partitions at each new time point with the latest traffic data. So at this point of time, we have a given set of partitions. This I-1 indicates the previous time point, I-1. These are the set of partitions given at the current time, based on time t-1. And the properties are high intra-partition homogeneity and high intra-partition heterogeneity. Now, our objective is we fix the number of partitions to k and incrementally update pi-1 to pi based on the new traffic data at time ti without repartitioning the whole network. So before starting the method, before going into the details of the method, let me explain about the boundary nodes. So when we partition the graph, there are some nodes which share which have neighboring nodes lying in a different partition. That means these nodes lie on the boundary, and these nodes have higher chances to move in to other partitions in the next point of time. Only after this boundary node moves to the other partition, to the neighboring partition, the internal node will be exposed as boundary nodes, and they will be able to move into other partition only after they are exposed as boundary nodes. So basically, the processing of boundary nodes have to be done first, and we need to check whether this boundary node is likely to move into other partition in the next time point based on the traffic data, new traffic data. Our idea, we compute the mean of degree of saturation of each partition and the volume ratio of each partition at the new time point ti. Identify all the boundary nodes and compare the degree of saturation and volume ratio of each boundary node with that of the mean of each partition. Then assign these boundary nodes to the partition with which this node is having a minimum distance. Now, this again is it involves a lot of tasks to compare each node with each of the partition to improve its efficiency, so that we can deal with the incremental update in real time. We develop an efficient solution where we first identify the least stable nodes. By least stable, we mean that these are the nodes which are highly likely to move into other partitions in the next time point. So we prioritize the processing of least stable nodes first, and then only we move on to the more stable nodes. So our implementation is based on a main heap tree based priority queue, where we put on queue. We put all the nodes, all the boundary nodes, in a queue based on their stability. And how do we identify the stability of a node is based on this measure we have developed. So let's see what this measure is about. This measure consists of two parts. First one is the temporal stability, which comes from the previous time point. So how stable was this node in the previous time point? We consider that as one part. And the second part is the spatial stability. By spatial stability, it means how close is the traffic measures of this node with the partition means. Here, this part is for the volume ratio, and this part is for the degree of saturation. We take the average of them. So this part accounts for spatial stability, and this part accounts for temporary stability. And finally, we get this measure the combining stability of this node, and based on this measure, we maintain the priority queue based using a mean heap tree. Yeah. Now moving on to how do we, after we get in this in this step, we keep on processing all the nodes until we reach to a stable node, until all the unstable nodes have been processed, and ultimately we after this step converges, we have produced the set of partitions of as the final result of incremental maintenance. Then after we have generated those partitions, we want to identify which of them are congested. We need certain statistical measures to identify whether to say a partition is congested or not. So for that, we have defined certain measures here. How can we say that a road is congested? So these are the two conditions that we have considered. If the volume ratio of that road is greater than a certain threshold, and the degree of saturation is greater than a certain threshold, we consider that road as congested. Then we define congestion ratio of a partition, which is the ratio of the number of congested road segments to that of the total number of road segments. This gives us congestion ratio. Then we use this measure to define congested partition. So whenever congestion ratio of a partition is greater than or equal to 0.5, we say that this partition is congested. Otherwise, it is considered as non-congested. We have used several visualization schemes, and they are mentioned here. A simple heat map where we just visualize the traffic measures of each road segment on the network using different color schemes. Then the second scheme is the partition visualization, where we visualize all the different partitions in different colors. The third, where we visualize only the congested partitions in the map. Then we have certain statistical measures which give an information about how the congestion is spread on the network, which give us further information on top of the visualization. So the first one is the congestion size in terms of road segments, in short form CSR. So it is the number of road segments in congested partitions. The second is congestion size in terms of partition. It means the number of congested partitions. Then we have congestion magnitude, which is the average of congestion ratio of all the congested partitions. So at a point of time, we may have multiple disjoint partitions as marked as congested, and this congestion magnitude actually considers the average of congestion ratio of all those congested partitions. Then in the last measure, average congestion ratio it refers to the average of congestion ratio of all the partitions. So basically, it considers the whole network instead of only the congested partitions. Now, moving on to the experiments, we have performed experiments on the SCATS data collected from Melbourne Road Network. It comprises of 1,444 road segments and 581 intersection points. And the traffic measures are logged by 493 SCATS sites. working of our framework. Uh, in the setup, we have formed batches of traffic data of every 3 minutes interval. That means that we accumulate the traffic data in every 3 minutes period, and use them in the form of batches to incrementally update the partitions. The computation time in the initial partitioning, it takes our method takes 92 seconds to partition the considered network. So then after, for the incremental update of partitions, it takes 1 second to perform incremental update, then less than 1 second to identify the congested partitions among all the generated partitions using the statistical measures that I explained before. Thus, we see that at each 3 minute interval of time, our computation takes less than 2 seconds, which makes it very much applicable to real scenarios, and much scalable to the urban scale networks. And in the following slides, I will explain the results that we got. Here in this slide, I have shown the result that we obtained from Google Traffic, that we see the visualization from Google Traffic and the visualization of our framework. So in figure A, we see that Google Traffic just visualizes as the real-time traffic in the form of simply heat map, where the highly congested where the road segments having high traffic are marked with are shown with dark red colors, and those having low traffic are shown in light green colors. One thing we see here is that even though two road segments, if they are marked in the same color, if they are shown in the same color, it does not necessarily mean that they are resulting out of the same congestion. They may not be connected, they may not be a result of the same congestion. Whereas in contrast to that, in our visualization in figure B, we have visualized in the five different partitions, where the one in the dark red is highly congested, is the most congested partition, and the one with the light green is the least congested partition. The information that we get from our visualization is that we can understand how a congestion is spread in a network. Normally, when we talk about congestion, it is not just one road segment, it is actually spread over a subnetwork or a region affecting multiple road segments which are connected. So this information is not being clear in the Google Traffic visualization. So in contrast to that, in our visualization, we are able to show that how a congestion is spread, or how many different congestions are there at the moment in the network. Also, yes, this is the zoomed view of our visualization, where these two parallel lines, they actually show the oppositely directed traffic flow. So we consider the two opposite directions as different road segments. So we can see clearly that not necessarily the two opposite directions will lie in the same partition, because they generally most of the time they will have different traffic measures. So the beauty of our visualization is the way it shows how a congestion is spread. Now in the next slide, we see we use our framework to study do a case study about how we have found some interesting patterns using our framework, that how congestion is forming in the morning hours. At 7:21 a.m., we found that this Monash freeway, at this point of at this location, the congestion starts developing. Then at 7:39, we see that the congestion starts forming in this direction. Then at 7:45, we see that it has formed a loop in the anti-clockwise direction. This is an interesting pattern that we see here, how it is growing in the morning, growing in the morning. Then in the next at 7:51, we see that there is another congestion developing in this eastern freeway, which is even bigger than the Monash freeway congestion, and having a higher impact on the road network, on the overall network. Then in the next time point, we see that these congestions have grown from their locations and merged with with all the different congestions, and the whole network is congested at this time point, 8:24 in the morning. So it is just some analysis on how the congestion is spreading in the morning, and we have further interesting results presented in the paper. Now moving on to the statistical measures, we see the four we see here the measure of CSR, which is a congestion size in terms of road segments. So we see in the morning at 7:33 there is no congestion, then it starts developing, then it keeps on increasing at 9. It has reached very high. In this way, the congestion keeps fluctuating during this period, after which it starts getting low. Then this is congestion size in terms of partitions. That means how many partitions at this point of time are congested. We see here that it is one partition congested at this point of time, then it is two partitions congested, then it 3, 4. It gives an information that how many different congestion hotspots have developed in the network at this at the current time point. In this figure, in figure C, we see there are two curves. First one in orange is the congestion magnitude. Which is congestion magnitude. As I mentioned before, is the average congestion ratio in the congested partitions, and the green one is the average congestion ratio in all the partitions. We see that there is a big gap in between these two curves, and which is actually the room to optimize the traffic flow. The bigger the gap, the more there is room to optimize the traffic flow. We can distribute, if the traffic management is able to distribute the traffic flow, it can be, these two curves can come close towards each other, and it gives an indication of how much we can improve the traffic scenario. Yeah, in the next figure, we actually, this figure tests how much accurate is the proposed framework. One thing we have found that there exists some previous works on spatial partitioning at a particular point of time, but we could not find any work that actually tracks the evolution of those partitions or incrementally updates those partitions. Therefore, to identify how much accurate our proposed method is, we have shown it in terms of these two measures. The curve in orange color is the percentage of congested road segments in non-congested partitions. So what is the percentage of road segments which are wrongly put in the non-congested partitions, and what is the percentage of non-congested road segments in the congested partitions, shown by the green curve? We see that this CRNP, which is congested roads in non-congested partitions, goes to a maximum of around 33%, and NRCP goes to a maximum of around 15%, which is which indicates which indicates the accuracy, the good accuracy of our proposed method. Yes, so this was all about about our method. Now, to conclude with, I'm just summarizing what we have done in this work. We have developed a framework for identifying and monitoring the congested partitions. Basically, our idea here is that we treat congestion as a congested subnetwork affecting multiple multiple connected road segments, and our aim is to identify and track those subnetworks. Then we have been able to capture the spatiotemporal evolution of congestion patterns as demonstrated through the experiments. Our sorry, is there a technical problem here, I guess? Okay.
So we lost your screen, Tarique.
Oh, okay. Yeah, actually, in my laptop, there is some, I don't know what's happening.
I think your laptop also lost connection.
Okay. Anyway, this is just the conclusion. This is in the experiments we have found some interesting results, which I have shown in the presentation. And then the computation time is very much within the scope that it takes less than 2 seconds for every 3 minutes interval of traffic data, which shows that it is very much applicable in real environments for smart transportation services. It can help in 2 ways. First is to develop better and smart traffic management services, and second is it can help in providing better smart services for the travelers, so that they can plan their journey, and they can use this information for real-time traffic information to plan the journey. So this is all about my presentation. Thanks a lot for your attention, and if you have any questions, I'll be happy to explain. I'll be happy to answer them.
Thank you, Tarique. And does anybody of the audience have any questions? If you do, please unmute your mics and ask, or you can type your questions in the chat box. Right. So while we may get questions, I do have a couple quick questions. So you mentioned the number of partitions K. So my question is, how do you, so the way I understand it is that you pre-specify the number of K partitions before actually running the algorithm. Is this correct? And if so, then how do you specify this number?
Yes, that's correct that you mentioned. We actually experimentally set certain value of K. So in the beginning time point, we start with the value of K, which gives us the best quality of partitions. And to know about this quality, that which value of K gives us the best quality of partitions, we have a measure which is explained in our paper, in a referenced paper that has been published in ADBT conference. So in that paper, we have developed this measure that helps us to identify which value of K is the best suitable at a particular point of time. And then after using that K, we move on for the incremental update. We apply the initial partitioning, and then we move on for the incremental update. During the incremental update, we use the same value of K, and it keeps on updating those partitions.
So do you think, so would changing the value of K from between from every time step to the next. Do you think this can improve the model, or does it have to stay constant?
The model is there, but by selecting different value of k, it may give if we are able to select the right value of k, which gives the best quality of partitions, that would give better results. So it is also apart from the model, from the framework that we have, we also need to do some experimental analysis that says the right value of k. And yeah, the final results are depending on k. So yeah, that is an important part of this work.
Thank you. Any other questions from those